Hello, and thank you for joining me. My name is Shauna Marr, and I would like to talk to you about my summer with the McNair LSAMP program. I would like to give a special thanks to the Rochester Institute of Technology, Monroe Community College, the C-STEP program, and my mentor, Dr. Jennifer O'Neill. In 2008, the Grand National Academy of Engineering outlined 14 game-changing goals for improving the life on the planet. We broke this down into 4 main categories: sustainability, health, joy of living, and security. If you'd like to learn more, check out the website below, but my talk today is going to focus on health. We know that people differ in susceptibility to disease and responses to medicine, yet there's little guidance for understanding and adjusting to individual differences. Treatments have been generally standardized for the many rather than the few. And in addition, there's very few methods which are needed for delivering personalized drugs quickly and efficiently to the site of the body where disease is localized. Also, innovative technology is needed to replace animal modeling and experimental studies, especially in pediatrics, due to ethical considerations. My project focused on new and effective ways to deliver treatments to the pediatric lung and airways. Some key facts are that there are many factors that lead to disease in both adult and children. However, many of the treatments for adult are not as effective as children due to several factors. In addition, there's a lot of diversity in pediatrics, ranging from premature neonates all the way through young children. And the fact that aerosol deposition may also be affected by disease states, such as increased inflammation due to diseases, compounds these issues. Also, we know that there's developing lung geometry that changes throughout the aging from pediatrics to adults. Lower respiratory tract infections continue to be the leading cause of death in pediatrics worldwide, yet little research has been done. We are investigating how to effectively deliver treatment to the lungs that are appropriate for different age groups, especially under age 1 and throughout different disease states. My project's broken down into 2 separate aims. First is to focus on personalized delivery. We look at, is there a significant difference in how aerosolized drugs are delivered into lung and airway of pediatric patients? In order to do this, we need to develop or determine if one has already been developed and is feasible, a 3D printed bio lung model. And we did this through a literature review of what is currently known and available. The second is to determine if this model can replace animal studies of particle deposition and age-related geometry. The second aim of our project is to understand the fundamental physics of the jet nebulizer to improve effectiveness in pediatric patients. In order to do this, we reverse engineered the Hudson Micromist jet nebulizer and modified its components using computer-aided design and 3D printing. What we then wanted to know is, does these modifications change the current drug delivery dosage and treatment regimen at the different stages of development and disease? Our objectives are to elucidate the fundamental physics through a series of experimental studies, to determine the effect of these modifications made to the nebulizer for improved functionality, and also to create a standard to collect and analyze data in the field of spray physics as it pertains to aerosols for medical treatment. Our first aim was to look at the literature and see what's being done as far as bioprinting and if it's possible. And what we did find in 2021, that we are now able to automate high-resolution deposition of alveolar lung cells by drop-on-demand inkjet printing, and this can recapitulate the structure even better than 2D printing and 3D non-structured printing, which is already in existence. This model can reproduce practical tissue-level responses to influenza infection, and the technology is able to be customizable, scalable for manufacturing and standardization, making it a great alternative to traditional models for pathological and pharmaceutical applications. Moving on to our second aim, we begin to break down the jet nebulizer, which is commonly used in pediatric patients. However, it's just that we're wondering if we can make it more effective. What we know about adults is that the optimal particle distribution size is between 1 and 5 micrometers. That larger particles greater than 5 micrometers will deposit in the upper airways, while smaller particles tend to be exhaled. However, we have very little to no information about particle sizes and deposition in pediatric patients. In addition, the equipment for the nebulizer is very heavy, loud, time-consuming, and difficult to coordinate even in adults. Compounded by that, output and particle size can vary greatly between the brand and type of compressor and the brand and type of nebulizer. Currently, there are no industry standards for best combinations for case-by-case regimens. Our project aims to break down the component parts of the Hudson Micromist nebulizer. And we did this by breaking it down into 16 different parts that make up this nebulizer. And we began piece by piece printing different iterations of the nebulizer to determine inlet air pressure, continuous bursting, pulsating flow, fluid fill height, cup position, and fluid type. These are all different independent variables that we are investigating and in the process of investigating. Well, this summer we've been able to print and collect data for the first 5. Our experimental design is to make changes to the Hudson brand nebulizer unit using the computer-aided design and 3D printing. Then the resulting droplet size is measured using the Sympatec laser diffraction system with air supplied by a pulmonal aid compressor versus shop air. The results from the modified parts are then compared to baseline nebulizer, the Hudson Micromist, using analysis of variance ANOVA testing in Minitab program to determine if there's a significant difference between changes in the different parts of the nebulizer that lead to possibly better particle deposition. All independent studies are first checked for normality and equal variances to ensure that they fit the model for ANOVA testing. Here we have a picture of our lab setup. And if you see here, this is our laser diffraction system on the left with a picture of the compressor on the right, and forced air actually is cut out of the picture. However, if you look closer where the jet nebulizer is stabilized and then the particles are passed through a laser, which is then collected and uploaded into the Symantec software and then later analyzed. The resulting measurement is droplet size, and this is measured using mass median aerodynamic diameter, shortened by MMAD. When we collect the data, we then process it through different programs, and the first thing we want to check for in the data is normality. And that will let us know that it's okay to perform and that the parameters fit within the ANOVA testing. So for ANOVAs, the data has to be independent. The responses for each factor level should have a normal population distribution, which is what we use the Ryan-Joyner test to determine, and that distribution should have equal variances. So what is ANOVA testing? ANOVA is a statistical technique used to compare different variables of a study and determine how they are different from each other. When considering the fact we can assume that two possible outcomes, either there will be a change or an effect, or there won't. This is called hypothesis testing, where the null hypothesis is represented by no effect and the alternative is that there is an effect. One way ANOVA analysis is our first step into elucidating the differences between the component parts. So what we see here is an overview of how ANOVA works, and it's all based on integral calculus and the area under the probability curve for the values that are at least as far from the reference value as the observed value is relative to the total area under the curve. Now, the greater the difference between the observed values the less likely it's due to simple random chance, which is what we want to determine. And that's reflected in a lower p-value. So there's multiple different types of ANOVA testing. There's one-way ANOVAs, there's two ways, and then there's your MANOVA, which allows you to compare multiple variables. So for us, we started with the one-way ANOVA, testing independent variables after checking for normality. And we began by looking at the first inlet pressure at 10, 20, 30 PSIs. We also looked at continuous versus pulsating flow, and that is used to represent what you would experience in the hospital versus the compressor that you take home. We looked at fluid fill height volume to determine if it mattered how much liquid was actually in the nebulizer for particle distribution. Then we looked at the cup positioning, where we changed the angle or degrees to represent a baby that may be laying on its back or slightly raised, to see if that made an effect on how particle is distributed when we're thinking about what happens when we go out of the hospital and into the homes, if the baby is sitting upright or laying down. We also looked at and wanted to determine if tap water versus DI water versus saline, or the general medication to treat airway diseases is albuterol dissolved in saline, and if these particles actually changed versus in comparison to the base, which is deionized water. Next, we looked at the distance between the baffle and the green insert, which is what allows water to be drawn up into the tube and then particleized. And the original gap is 1774 micrometers for the original versus larger gaps that we compared. And what we found is that there are significant differences in almost everything that we looked at based on p-value, with the exception of the fluid fill height. It actually doesn't matter how much liquid is in the nebulizer to create the resulting droplet size. What is most significant that we found was the differences in baffle gaps. Well, we see here the original baffle gap size, if you reference back to slide 8, where this gap is highlighted here, that there is the greater the gap, the less effectiveness it has. So we come back to the resulting droplet size, and you can see that with the original, mist is approaching up to 5 inches, where as you increase that gap size, we begin to lose the force behind it, and we're only getting out to about 1 to 2 inches. And then with the modified gap at the biggest size, largest size, we see actually no particles being drawn up into the nebulizer to be dispersed. So our conclusions are that we found that there is the technology to have an experimental model to study deposition of particles in the lung and airway, and that begins to start making it possible to stop using animal studies, which we know to be limited, or human trials, which there's many ethical concerns, and instead start thinking about how we can use bioprinting to mimic the expected behavior in vivo. Second, we deconstructed the jet nebulizer to see if there is a way to make it more efficient. We developed statistical analysis and standards for data analysis. We did ANOVA and normality testing and analyzed 6 different variables and drew several conclusions. So far, the baffle gap variable seems to be the most significant in terms of design impact, with a bigger design being more inefficient, and studies to print and design a smaller gap are underway for testing. In the future, we hope to continue printing the 12 remaining variables and test for efficacy, especially the smaller baffle gap as we discussed, and we want to begin to understand what's the optimal particle size for pediatric patients and continue to develop industry standards for nebulizer physics and pharmacology, and also to continue looking into developing the 3D printed biomodel for ex vivo studies. I would like to thank my mentor and my lab mates for all the work that they had done up until this point and designing the different parts of the nebulizer. And it's been a great summer working with everyone. I especially want to thank Kate, Tori, and Joanna Victor at the McNair and LSAMP summer program for coordinating, and also the seminar coordinators. Also, Miss Deborah Joseph McEwen at MCC and CSTEP for all of her support, and a special thanks to Professor David Giroux for providing statistical analysis support. Thank you.